So once again, just we'll revise what are the things you are going to study in your first module, because you are discussing about first module. So first one is introduction to crystal structure, the coordination number, atomic packing factor. That there is a small derivation I am going to do in the next class. That is you have to derive the atomic packing factor for Bcc, Fcc, Hcp structure. And today's class you are giving how the atoms are arranged in those structures. At least you have to imagine it. Next class I am writing just I may show only the schematic sketch, handwritten sketch, and handwritten derivation for those derivation for atomic packing factor. Then you have to study the crystal imperfection. One is for formation of Bcc, Fcc, and Hcp. Already we have discussed. So from atomic level, the initially when metal is in the molten state, atoms are randomly moving. Only when it solidifies, or we can say that when it crystallizes. So then, depending upon what type of material you are freezing or crystallizing, you will get Bcc, Fcc, or Hcp structure. During the process of hoping that all atoms are oriented perfectly, and each and every corner there are one atoms in simple cubic structure or Bcc, Fcc, etc. There are some certain the location where atoms are there in simple cubic, Bcc, Fcc, and Hcp structure. This is the theoretical concept. Or ideal case, once you say simple cubic, all 8 corners there are one atom. But it is not true, because of during solidification there may be many other parameters which affect the rearrangement of atoms, especially when you going for sudden cooling, very fast cooling. So most of the time fast cooling takes place, you are not putting water, or you are not keeping molten metal in the freezer. So once metal is in the molten state, once it is poured into the mold, or it may be metal mold or it may be sand mold. So the temperature difference between the molten metal and mold wall is the huge temperature difference. Because of that, the immediately heat is transferred from molten metal to the mold wall. Some amount of heat is exposed to the atmosphere, or ambient the atmosphere. If it is open mold, it is some amount of heat is lost to the surrounding media, surrounding. But so there are one more type of molding, that is referred to closed molding process. So that again you are going to study in your casting. One is open molding process and one more is closed molding process. What are the experiment you are doing in foundry and forging lab? It is mainly concentrate more on the open mold process. It means molten metal is, even you are pouring, it is like putting coffee from jug to coffee glass. The top surface of the coffee or tea or hot milk is exposed to the atmosphere. In the similar way, when once you pour the molten metal into the mold, the surface of the molten metal are exposed to atmosphere. Then it is referred as an open molding process that you are going to study in casting. I'm not going to discuss about it. There is one more closed molding process, where heat is transferred to the surrounding medium or atmosphere through the mold wall, because your molten metal is totally closed all around. Initially, there is a small opening, like putting coffee into the flask or the thermal flask and tighten the cap. Then your coffee is not exposed to the atmosphere direct. There is no direct exposure to the atmosphere. If you put it in the regular glass, then one top surface of the coffee is exposed to the atmosphere. But once it is closed, cap is closed in the thermal flask, then it is not exposed to the atmosphere. So yeah, whatever the amount of heat is transferred from the coffee or any tea, so through the walls of the thermal flask. In the similar way, in the case of closed mold process, heat is lost by the molten metal goes to the atmosphere through the mold wall. Well, that means we can say that So there may be one, there are some cases, there may be very fast cooling. Molten metal will be cooled fastly. If you use metal mode, metal means metals having more thermal conductivity compared to ceramic material. If you use metal mode, then there is a cooling rate is very fast. During cooling rate, during the process of cooling or recrystallization process or crystallization process or solidification process, there may be some atoms may not occupy the original lattice structure. Original lattice structure means once you say it is a simple cubic structure or 8 at corner, that should be one atom. Instead of 8 atom, you may get only 7 atom because of fast. There is no sufficient time is given for rearrange the atom. So then some amount of imperfection may take place or defect maybe takes place. The defect quantity of the defect is very high. If you consider 1 centimeter by 1 centimeter by 1 centimeter cube, the microscopic defect may be some the few thousand to up to few lakhs. The defect level is very high. But what you studied in your physics, chemistry, or physics, so you are saying FCC, BCC, HCP structure, that is the ideal structure or critical structure. So because of many other parameters, I have given some of the example of fast cooling, etc. There may be some defect reform in the metal. Those defects are referred as a point defect, the line defect, surface defect, and volume defect. I think volume defect you can understand, especially if it happens in the casting. Some space there is no the molten metal. Because of contraction, etc., there may be small voids or holes inside the solid metal. Then it is referred to the volume imperfection. Huge amount of atoms are missed in some region. Surface defect, there may be defect in the boundary. I am talking about the boundary because why I am telling is, so what I am telling in the last few classes, those are the fundamental required. Not only the first chapter, many chapter may be required. So whenever you are saying surface is a outer surface of the material, or at the grain boundary. You are talking about the crystal or grain. You have sodium chloride crystal. That outermost, if you consider only one crystal, it is outermost surface is referred to the grain boundary. Even in the case of the diamond crystal also, you are not talking about the surface means don't think that it is surface defect. So you are doing some machining process or casting, there may be surface defect. Those are the macroscopic defect. In the casting also you are going to study about the surface defect. In welding also, during your welding process, there may be a surface may be rough. Those are referred to the macroscopic defect or visible defect. Even if you go for a turning operation like lathe operation, drilling operation, there may be defect on the surface. Those are the macroscopic defect. Here in the imperfection or crystal, we are talking about the crystal imperfection. So when crystallization takes place, during the formation of the crystal itself, some defect may be formed. That is, you are talking about the crystallographic level or in the grain level. So then it is then those are the defect you are going to study. You are going to study not in the macroscopic defect. It is clearly visible from our naked eye or some other some low magnifications, microscopes. Those are the defect. Line point defect means if one atom is missing from the corner of the simple cubic, then it is referred as a point defect. The one line of atoms are missing in a lattice structure or in a crystal structure, then it is referred as a line defect. Always you have to, when you are defining, you have to say lattice structure, crystal structure, or crystal. Don't say in metals. Most of the definition, if you say in metals, in solid, in workpiece, in sample piece, so that type of answer most of the students will write in the examination, even for the test. No, you cannot write like this. If one atom is missing, or carbon atom is missing, or any one of the atom is missing from the unit cell or crystal structure, then it is referred to the point. If line of atoms are missing, then it's referred to the line defect. On the surface means not on the, you are talking, not, imagine you have one metal rod. So you are not discussing about the surface. What are the defect present in the outer surface of the metal? You are discussing about the defect on the grain boundary or surface of the grain. those are defect as surface defect. So don't think that surface defect means the defect in the outermost surface that is visible. No, it is not like that. There is a one more process, that is the diffusion process. The diffusion process, there is a small derivation that will do derivation, but first try to understand this concept. Then derivations available. I'll put PPT and I'll explain those simple derivations, not so complex. But when you are reading textbook, finally for the examination point of view, examination time you are reading the textbook. Even for the during test time also, you are reading the textbook only. You don't have sufficient time to the reason this video, even though every day I'm putting in Google Classroom, but you will not get. Imagine during the examination time, there may be around 40 hours video. It is not possible to listen to those videos. So understand first, then read the textbook. If you have any difficulties, run the videos, and those points you can understand. So derivations are very simple, not so complex. Once you understand the concept, then deriving will be easy. That I'm doing the derivations. So why I'm telling all those things means I'm doing so a lot of other fundamental aspect of microstructure, grain, crystal, polycrystallines, etc. Then exactly when you understand, when you're teaching those concepts, you should know where exactly these concepts are used. Now there is one more phenomena. It is after the diffusion process. So there is a process of mixing two gases. That is also a diffusion process. One gas is diffused into another gas. That's a gaseous stage diffusion process. Or if you can put some gases inside the liquid also, then that is also a diffusion process. And easiest way to remember, and repeatedly I am giving example is, imagine you have one glass of water, transparent glass. You are dipping one drop of ink into the water, glass of water. So at that particular point, just once you dipped into that concentration of the ink is very, very high on that particular point, or location, or area, or region. After few seconds or few minutes, ink is spreads across the complete liquid. So that means the ink is spread. There is a diffusion. Ink made up of liquid ink made up of a lot of atoms. The atoms are diffused or spreading around the liquid. So then it is after liquid state diffusion process. Putting one drop of wine, slowly the concentration will be decreases. The initially concentration gradient, you are talking about the concentration gradient. The concentration gradient is very high at the difference of concentration of ink and surrounding area. The concentration is very, very high. The difference is very high over a period of time. So once ink is mixed thoroughly with the water, the concentration of the ink is almost uniform throughout the glass of water. Once you spread it, once it's automatically spread or even stir it, the concentration of the ink is same. So then there is no the concentration gradient. That is after C is the concentration. We are using the notation C. The change of concentration is given by dC. Your differentiation is nothing but a change with respect to the distance x. We have concentration C. The dC refer to change of concentration. It also takes place with respect to time also, with respect to distance also. Then this is after dC by dx or dC divided by dt. There is a steady state flow and unsteady state flow. Can you give an example for steady state flow and unsteady state flow? Any example, not necessarily it is a material science. You studying those concept. One example, steady state flow and unsteady state flow. Can you think about even if you simple the bathroom taps, if you slightly open, the initially water flow rate is very, very small, less. Once it is completely open, the water flow rate is initially is very, very slow. Then it increases. It reaches one state. Then it is after the steady state. After complete open, after a few seconds, after complete opening of the tap, flow rate remains same. There is no change. Initial flow rate is less. Once it is completely open, flow rate increases to certain value. Imagine initially flow rate is 0, that is there is no flow of water, that is 0. Then it reaches to 10 in it. Then you want it to completely open, the 10 remains same with respect to time. That is about a steady state flow, a steady state process. But initially there is a transient flow. So again there is a diffusion law. There are fixed law. It is about a fixed law, first law and second law. The first law refers to steady state flow. So in the later stage, you are going to study about the water turbine. So most of the water turbine, water is entered into the turbine with constant flow rate. The flow rate is constant. The amount of water entering into the turbine with respect to time per second or per minute remains same. That is the example for the steady state flow. There is an intermittent flow like intercombustion engine. Only during some stroke, the fluid air is entered. Suction stroke, only air is entered into the system or your cylinder, or some fluid is even fuel is entered into the cylinder only a certain time. So now afterwards it will stop. That will not comes under your steady state flow. Those are comes under unsteady state flow, or we can say that intermittent flow. So that means there is a diffusion, but when you come, those are the general. I am talking given the example what is diffusion process. Those are, you can imagine, you can visualize those process, because once you drop ink into the water, ink will spread. We can imagine. Or if you put during holy time, you are putting some colors to the liquid, the water, then after a few seconds, color of water becomes red or blue depending on what type of powder you are mixing. Those are clearly visible. Those are liquid state diffusion process. If then you imagine in the hostel mess, if they are cooking some nice items, without entering into the mess, you can feel what is the smell by seeing the smell. They are cooking in some place, but you are getting smell in some other place. That those will comes under the gaseous state diffusion process. But as per your material science is considered, you are talking about the solid state diffusion process. You cannot use, and now it is very difficult to imagine what is solid state, the diffusion process. So already metal is there. Imagine you are given a piece of metal at room temperature. Already you are defined in metals at room temperature or at lower temperature. The atom positions are fixed. It may be Bcc, Fcc, or Hcp. Atom positions are fixed now. Then to get diffusion, it's a flow of atom. Whether it may be liquid state also flow of a movement of atom. Even in the gaseous state also there is a movement of atom. There are some tragedy recently in Andhra Pradesh. There is a gas leakage. So that is the diffusion. Gas is leaked in some factory. It is diffused to the surrounding area. So those you can imagine. But when you come to solid, you are given some piece of metal. As per theory, theoretically, you are saying that atoms are fixed. There is no movement for the atoms at room temperature, but still there is some atom movement of atom. The movement of atom in the solid materials, or in the especially in the metals, you are discussing in your atomic diffusion process. So you have to imagine, even in the metal is in the solid state, the atoms are moving from one position to the another position. We cannot use the term position. One lattice structure to the another lattice structure, or one unit cell to the another unit cell in the crystal structure. Those type of words you have to use when you're talking about diffusion. Don't think right movement of atoms in the metals from one place to the another place, or one position to the another position. If you ask for the definition of diffusion, maybe 1 or 2 marks, you don't get. If you say explain the diffusion process, if you write in general, the movement of huge amount of atom from moving from one place to the another place, or one location to the another location, or one position to the another position, you don't get the marks. You have to say movement of atom from one crystal lattice or unit crystal lattice to the another crystal lattice in the crystal or in the grain is referred as atomic diffusion. What you are discussing is, it is only the solid state diffusion process. So there are some one or two derivations that is it does not take much time. It is not so difficult. Next is in the second part. One. In the second part, you already discussed. So mechanical behavior of the material. So mechanical behavior already you are defined. Stress is load divided by area. This is formula. Or you can say that it is a resistance offered by the material or external loading. There is a strain. There is a formula for the strain also we have discussed. Change in length divided by the original length, or deformation divided by original length. Then you have to study the stress strain diagram for ductile material. Can you give one example for the ductile material? One example for ductile material. Ductile material. One example.
Brass, aluminium.
Which one?
Brass, aluminium.
Aluminium is an example for ductile material. Glass is example for brittle material. Okay. Now, engineering stresses and strains. So there are two stresses. One is engineering stresses and strain. There is one more true stress and strain. The engineering stress and true strains. Strictly speaking, it is the engineering stresses, engineering and true stress and strain. Forget about that. So what most of the time, so what you conduct calculating in your material testing laboratory, that is comes under engineering stress strain diagram or conventional stress strain diagram. Conventional stress or engineering stress and engineering strain. So later stage you come to know that when you pull the rubber band, imagine diameter is around 3 of that will be around 5 mm. Once you pull, length increases, diameter decreases. During the process of applying load, the diameter is decreases. The original diameter, but when you conducting the experiment, you are noting down some values, the initial diameter of the specimen, and force load is stress is given by force divided by area. Force divided by area, but force divided by original area. We are talking about the force divided by original area. The stress is equal to given by force. Engineering stress, I am talking about the engineering stress, is given by force divided by the original area. That is referred to the engineering stress. Strictly speaking, once you define engineering stress, the force divided by original area. But when you pull in the rubber band, the area is decreases. Diameter of the rubber band decreases. That you are not considering in the case of engineering stresses. You have to remember, once you say engineering stress throughout your 4-year course, most of the time you are considering only the engineering stresses. There is one more type of stress, that is referred to the true stress. During the true stress calculation, you are forced divided by the cross section of the material at that moment of time. You are pulling the rubber band, initial diameter is 5 mm. For 1 kg of load, you are considering 1 kg divided by 5 mm diameter, 5 mm square, that will be 5 mm square. Once you apply the load, diameter decreases. So you have to consider the area of the cross section at that instant of time. Then it is referred to the true stress. Engineering stress means the denominator is always original dimension or original cross section area. In general, you can remember. True stress means the load remains same. In the numerator, that's a load. In the denominator, load divided by area. The area is instantaneous cross section area at that particular load. If you apply 1 kg of load, the diameter may be 5 mm square. If you apply 2 kg of load, diameter may be again 5 mm square. If you apply 5 kg of load, the diameter, this area will become 4 mm square. It will be elongated because diameter decreases. That change in cross section area you have to consider in the case of true stresses. And we know the definition of the strain. Strain is given by load divided by this change in dimension divided by original dimension. That will be original dimension. That is the engineering strain. In most of your mechanics of material, you are talking about the stresses and strain, except few cases, you are considering only the engineering stresses and engineering strains. But when you are considering engineering true strain, the change in length divided by the length of the specimen at that particular moment. Imagine you will find out the initial length of the rubber band. That is the original length of the rubber band. For true engineering strain, the change in dimension divided by original length. Denominator remains same, original length remains same. But if once you apply 5 kg or 2 kg of load, the previous 4 kg of load, when you apply 4 kg of load, dimension is different. When you apply 5 kg of load, dimension is different. So for that, so you have to consider original length as the length in the previous stage of loading. That it is a little bit difficult, especially for the true strain. Anyhow, you have derivation, we are going to do derivation. But in general, at this moment, you should know the engineering stress is given by load divided by original cross section area. Engineering strain is equal to change in length for time being, change in length divided by original length. That you have to remember for engineering stress and strain. But when you come to true stress, the load divided by original not cross section area at that particular moment. That is your true stress. True strain means the change in dimension divided by the dimension of the specimen or length of the specimen at that particular moment is true. But there is a practical difficulty in finding out the change in cross section area or change in length, because once your specimen is mounted in the tensor testing machine, it is very difficult to measure the how diameter changes. Diameter changes continuously. We require some sophisticated instrument to measure change in dimension. But original dimension, before conducting the test, we can use your vernier caliper or micrometer, etc. We can find out the initial dimension. But changing the dimension when you apply the load, it is very difficult to mount any strain gauges or any measuring devices. That's why most of the cases you are going for only for the engineering stresses, even for the strain also. Then there is a linear and non-linear elastic behavior and properties. I have given the example of linear also. What is linear? I am giving the same example so that as per your engineering, your mechanics of material is considered design of machine element 2, or there is one more subject, that is a finite element modeling, that is a computer modeling. Everywhere you are considering any structure. It may be your axle. Axle is considered as a spring having stiffness K. The building column is also made up of building column is also modeled as a spring having some stiffness. The shaft is also considered as a material having certain stiffness. So now, when you're talking about the stiffness or the linear and non-linear, you're talking about behavior of the material. And given the example of spring. So once you apply 1 kg of load, the deformation is 1 mm, 2 mm deformation, 3 kg of load, 3 mm deformation, 4 kg of load, 4 mm of deformation. Like that, if you 10 kg of load, 10 mm deformation. If you plot load versus deformation curve, so we'll get straight line. It is normally 45 degree to x-axis or y-axis. Then it is what is the linear behavior. You study about line. Line is a linear element. Equation, the line is given by y is equal to mx plus c. That's a linear first order differential first order equation. So if you draw load versus deformation plot, if you get straight line, the behavior of the material is linear. For most of the metals, you studied about stress strain curve up to elastic limit, plastic limit. Your stress and strains are proportional according to Hooke's law. That is a linear behavior up to elastic limit. If you go beyond elastic limit, if you apply the load more and more, the material undergo plastic deformation. Because of that under plastic deformation, there may be you may not get straight line like a rubber, plastic. If you draw load versus deformation, you not get straight line. Instead of that, you may get curve. We are showing those four these plots also. Seeing the plot is you can understand better, but you have to understand this the fundamental concept. Then drawing plots, curves are not so much difficult. Everything is available in the books. I'll show those PPTs. Don't worry about it. So that means there are the mechanical behavior. The title of the chapter itself is mechanical behavior. Mechanical behavior is it may be linear or it may be non-linear. In simple way, your deformation is directly proportional to the applied load, then the material is behavior is linear. Your deformation is not directly proportional to the load. If you apply a small amount of load, there may be huge amount of deformation. After yielding, that will also happen. In such cases, it is non-linear behavior. There are some properties, stiffness. When we are saying stiffness is resistant to the deformation. You have to remember, stiffness is resistance to deformation. There is a toughness. Again, toughness is also resistance to deformation. But if the loading is within the elastic limit, you have to remember what is elastic limit. So once member is loaded up to elastic limit, the material undergo deformation like a spring. If you apply a small amount of load, it undergo deformation. If you remove the load, it come back to the original position because of the stiffness. But toughness, we are talking the material. When you apply huge amount of load, spring may bend permanently. So resistance to both elastic deformation as well as plastic deformation is referred as a toughness, like that. There is a yield strength, offset yield strength, ductility, ultimate tensile strength. All those things, once you know the stress strain diagram, I explain those stress strain diagram. Those are the property of the material or behavior of the material. Then you will understand with respect to stress strain, yield strength of the material, offset yield strength. Even you are conducting to find out ductility. Again, you are conducting tensile testing. Because your material science and your material testing laboratory are closely related. So there is a ductility. You have to find out the ductility. Imagine steel rod is given. You have to apply you have to find out what is the ductility. By conducting tensile test, we can find out what is the ductility of the material. You have to remember, we can find out the ductility of any material by conducting tensile test. There are formulas also available. I am not talking about the formula now. By conducting tensile test, we can get ductility. Then up to from this point to this point, up to toughness, you are studying about the macroscopic behavior of the material. So that means you are mounting a specimen. Imagine you are applying the load on the specimen. Specimen is metal specimen. It has many grains. It has many grains. We are not talking about the one single grain. So what is the overall deformation of the material? Not individual, the crystal level deformation. But there are many grains. Then to try to behavior of the many grain will be difficult, especially for writing some mathematical equation, etc. So you cannot predict what is the behavior of the group of the people. Imagine there are group of people, so it is very difficult to predict. There may be good people, there may be bad people, there may be intelligent, there may be non-intelligent, there may be hardworking, there may be non-hardworking group of people. Then getting conclusion, writing the equations, mathematical equation is very, very difficult. But in general, we can behave. The whole group is okay. General conclusion we can do. That is the macroscopic properties. What you studied from mechanical behavior up to tensile strength or offset yield point, ductility, ultimate tensile strength, your stiffness, everything is comes under macroscopic level of behavior of the material. But we are not studying about the crystallographic level or grain level. Grain means group of Bcc cell or Fcc cell, etc. But in the last para, you can see the plastic deformation of single crystal by slip and pinning. One side you are saying a plastic deformation. First, why I am telling repeatedly, I am using some word means first you have to understand what is the plastic deformation. Imagine you have steel rod, construction industry, they are using a steel rod. There is one person, the group of people, they are referred as a bar bender. It is one profession itself. So they'll bend the steel rod depending upon their requirement. There is some hooks, etc. They will pull, they will bend. it is a permanent bed, or it is permanently set. That is what is a plastic deformation or permanent deformation. The correct term used is plastic deformation. So you have the spring, you are applying the load, it will undergo deformation. And once you remove the load, it come back to the original position and position. Then it is elastic deformation. In the case of plastic deformation, it is a permanent deformation. We cannot, material not come back to the original position. Like your fracture. There may be aircraft landing, it something happen, it undergo fractures or it causes a lot of disaster itself. It will fracture. It will, even though afterwards it will not come back to the original position. Or original, it is recovery will not take place. So then it is after the plastic deformation. In foundry lab, you have to conduct one experiment. That is a forging experiment. There, you imagine steel rod is given. The original cross section area is the square, circular cross section area. So that we have to convert into rectangular cross section area or square cross section area. In the foundry lab, you are going to work circular cross section to rectangular cross section. We have given on, they'll give one specimen having a circular cross section. By heating the material to the red hot condition, you have to beat with the hammer. Finally, you have to reduce the cross section or transform the cross section from circular to a rectangular cross section. After hammering, so it will be always rectangular cross section only. You are like automotive bodies. Initially, it is a sheet, plain sheet, sheet or plate. It is bent using different bending operation. So it is permanently bent. Then it is about the plastic deformation. Now we are talking about the plastic deformation of single crystal. So you have to, once you say crystal, you have to imagine what is crystal. Crystal means, what is crystal now? Tell me. What is crystal consist of? What is crystal? Crystal consist of, I am saying crystal consist of.
Unit cell.
Arrangement of atoms.
Unit of atoms or group of atoms?
Group of atoms, sir.
Group of atoms, okay. But from group of atoms, now what is the next level of structure? Group of atoms will rearrange themselves during solidification, and it forms unit cell. So once you say crystal,
Cell.
Any doubt? Imagine we have a group of atoms. The atoms are moving randomly in molten state or in the liquid state at higher temperature. During the crystallization process, I am using the term crystallization process. That means it forms the crystal during the, it happens. We can use the term crystallization process only for the metals, most of the cases metals. But all material is not crystallizes. It may solidify from liquid state to solid state, but it not crystallizes. So it may be amorphous material. So during the process of crystallization, it forms unit cell. So yesterday you were talking about the nucleus. So the one unit cell, because one unit cell will be formed, one small, I am giving the example. First unit cell is almost like a small particle of ice in the water. That is the first unit cell. There may be n number of particle of ice in the cold water. Once if we keep it in the freezer. Those will act as a nucleus for the grain or different crystal. Then imagine there are 5 small particle of ice at different location. Some more water is joined and solidified. So like that, there may be one unit cell surrounding, some more unit cell will be joined. In some other location, one unit cell, it is solidifies, and finally it forms finally forms one more grain. That means your grain, even though you are saying it is a single crystal, don't think that it consists of only one unit cell. It has many unit cells even in the single crystal. Even though you are saying it's a crystal, even diamond crystal, it may be size maybe 1 centimeter or 2, sometimes 1 centimeter, 2 centimeter. It has many subunits. But when you come to metals, the one crystal or grain, it has many subunits. Those subunits are nothing but your unit cell. So don't think that once you say single crystal, don't think that single unit crystalline units. You are analyzing BCC structure or FCC structure. It is you are talking about the crystal. The crystal is also referred to the grain. So then finally in the macroscopic level, you are seeing some deformation. Material is pulled, the deformation may be 1 mm or 2 mm. But in the crystallographic level or crystal level, how deformation takes place. We have group of BCC cell, it is nothing but a crystal. FCC, that will be aluminum, if FCC cell. We can analyze the smaller and smaller substructure very easily. I am giving the example, same crowd, the analyzing the behavior of the crowd may be difficult. Analyzing the one person in the crowd, it may be easy. In the similar way, your metal is a polycrystalline material. Analyzing the behavior of each and every crystal may be difficult. But we can analyze a single crystal. That's why how deformation takes place in the microscopic level is for that we can study in the crystallographic level. That's why it is after the plastic deformation. One term you have to remember, there is a plastic deformation. It is a permanent deformation. There is no recovery. The material undergoes deformation. One load is exceeding your yield strength of the material, it will undergo plastic deformation. How plastic deformation takes place in the macroscopic level, you are studying about this, your elastic limit, plastic limit, your linear and non-linear behavior. In the macroscopic level, you are studying. In the crystallographic level, not in the atomic level, you are not talking about the atomic level. You are not talking about in terms of unit cell level, but you are talking only about in the grain level or crystal level. Whole material science is you are dealing in the microscopic level, not in the most of the cases, not in the macroscopic level, not in the atomic level or lattice structure level. You are discussing about the how transformation takes place, how grain is formed, how crystal is formed, how deformation takes place, how we can change the shape of the crystal, how we can change the size of the crystal. So we are studying one treatment, that is about the heat treatment. Even material testing laboratory also, you are studying the heat treatment process. So heat treatment process, we have the crystal is already formed during saltification process. By heating and cooling process, we can change the size of the crystal. We can change the size of the crystal in the during heat treatment process. So once you change the size of the grain and shape of the grain, it is not machining process. Imagine you have a diamond crystal, we can change the shape by special machining process. That is not like that. By heating the metal to the red hot condition and cooling fastly or slowly, etc., we can change the crystal. We can change the crystallographic structure. So then it is referred as heat treatment process. So in the similar way, we are talking about the single crystalline material. By slipping, the plastic deformation may take place by slip or twinning process. Then there is a mechanism of strengthening in metals. So that means we can make the soft metal into harder material into softer material. Everything takes place in the crystal level or grain level. So that means as per your first topic is considered, you have to derive your atomic packing factor for BCC, FCC and HCP structure. That's one part is left out. One derivation for Fick's law, the diffusion process, already concept of diffusion I explained. That is and some numerical problem you have to do here, and HCP and also you have to do. So then when you come to your deformation, this stress strain diagram, you have to do small problems. It is almost similar to what problems you are studying in mechanics of material. So then you have to study, there is some imperfection you have to study. This topic is left. It will require around 2 to 3 hours to complete your around 3 hours. Next weekend we are going to finish this first module. So again here is plastic deformation by single crystal. So you have to go for small derivation how deformation takes place. So now I think you can go back to your actual structure. I hope you understood what you are going to study, concept are required in the first module I explained all the concept, but you have to practice the diagram. You have to practice. I told you to purchase material science textbook by Punish. So diagrams are there, equations are there. Those first you have to read. You can, and all the concepts are there explained. Now you can understand better. You have to practice. Now you are talking about a crystal. This is one crystal. This is one crystal. This is one more crystal. This is one more crystal. This is one more crystal. These are the crystals. Now you can see. You can understand this diagram. You have polycrystalline material. This is one crystal. This is one more crystal. This is one more crystal. These small boxes refers to your unit cell. Small boxes refer to unit cell. This is one grain. This is one more grain. This is one more grain. Grain and crystals are same. Even though it is amorphous, you can say that this is one crystal. You are talking about the surface defect. This is the crystal surface. The grain boundary surface. This is the grain boundary surface, or it is a crystal surface. This is again the crystal surface. This is this boundary. You have seen the line, no? Inside there is a BCC or Fcc structure, but there is a crystal structure. This is one crystal. This is one more crystal. This is one more crystal, and each grain or crystal is surrounded by the boundary. It is the grain boundary. Like we have India, we have, if India considers one boundary with respect to world, one crystal. So India has its own boundary. One side there is a China, one side there is a Pakistan, etc. That is the boundary. Like Karnataka also there is a boundary. For some neighboring state also there is a boundary. So there is a common boundary between Karnataka and Maharashtra, or Karnataka or Kerala, Karnataka or Tamil Nadu. Those are the boundary. Imagine this is one grain. It is a map, India map or world map. This is one crystal or grain. It is surrounded by one more grain. So those two grains are separated by the grain boundary. There may be some amount of grain boundary defect. You can see here at the grain boundary, atomic distance is not same, because nucleus for this grain will be different, because during solidification nucleus for this grain is different. So because of the difference in nucleus formation at the grain boundary, there may be defect, there may be some problems. Like India China border, there is always some issue. Like it's a boundary. Like India and Pakistan border, always there may be some issues, because India is originated with different policy or democratic principle, and China is originated on communist principle. Like that, in the metal also there are different nucleus. The nucleus growth of the nucleus is having different phenomena. Because of different growth rate of growth, at the grain boundary, the distance between the atoms are different. Because of difference in atomic distance, the force of attraction, we know from the physics, force of attraction is directly proportional to atomic distance. As atomic distance changes, the force of attraction or force of repulsion also changes. A force of attraction or repulsion also changes. So hence there may be defect in the grain boundary. So that means what you have to understand the concept, then examination point of view, test point of view. So you have to draw these sketches, you have to explain the concept. Okay, today I'll stop. If you have any difficulties or any doubt, you can clarify now. There's some numericals, problems and derivation you have to do. That we'll discuss in the next class. That's not difficult, but understanding the fundamental concepts are important. These same concepts, same terms you are using throughout your semester till end of your semester. The same properties you are studying in other subject also. Whether you're doing masters or doctorate in that area, again you are talking about stresses, you are talking about study strain, you are talking about the different properties and testing material. Maybe fatigue testing machine. You've seen aircraft fatigue testing machine. How fatigue will be formed, how fatigue, everything you are talking about with respect to microscopic level. Once you understand microscopic property in the microscopic level, macroscopic property we can determine by using different machine. Okay, those are not entered your USN number, just enter, then you can leave the session. this regularly updating video in the Google Classroom. Those who miss, if you don't understand some concept, you listen. If you want to listen that video day to day itself, it's a reason that is easy. At the end of the semester, it may be difficult. That empty lab PPT, I'm putting in it in Google Classroom for empty lab. You can refer also.
So can you post this notes also, sir?
Notes, I think next week I'll post the notes. Huh?
Okay, sir. Okay, sir.
Not PPT, I will post the notes. Huh?
Okay, sir.
I think I strongly suggest you to purchase Punish. First 3 modules refer Punish. It is very clear. All points are given, all information are given. Purchase that book. Huh? If something is missing, I'll give. But I have the handwritten notes. I'll put it in the group. But better to
Yes, sir.
purchase that Punish test.
Yes, sir.
During the semester beginning, I told you to purchase one more book, Chalister. If purchase, read like a story book in the beginning, so you'll understand the complete concept. But all points are not given. All information is given. Huge amount of information is given. Those information may not be required for your examination point of view. Hello. Hello.
Yes, sir.
No, for not for. So those are not left. I think.